So we can see the slide.
It's visible, no?
Yes, presentation is also there.
Okay. Okay, so let us start.
So
Yes.
Yeah, you can start. I mean,
we can start it. Okay.
Yeah.
Yeah. So good evening to all of you. So today I have exactly up to 6:30. So again, today's topic is also like quite vast. I mean, introduction to linear programming. So I have to keep only to the level of introduction, and that to introduction to only perhaps one aspects of solving linear programming problem. So what I have in mind is I'll show you maybe a couple of examples on how to formulate a linear programming problem. Of course, before that we'll discuss what are the linear programming problems, etc., and how to formulate linear programming problems or linear programming models. Then there are both graphical solutions as well as algebraic solutions. And of course, graphical solutions can be, obtained only for problems with two variables, because you can plot them in practice. In theory, to 3-dimensional solution of is the 2-dimensional it's a good amount of explain the problem is for multi-dimensional system. We are for multi-dimensional methods, we will use algebraic methods. One of those is known as simplex method. To show the for solutions of LP.
I think disconnected quite a bit.
For solutions of you asked if somebody knows one particular solution, yes, to show that basically it's the decision maker's choice. So as an optimizer, basically you would like to have points on all the Pareto optimal solutions will lie on Pareto optimal front. Okay, then the next decision can also only be taken up until I get certain inputs from the decision maker. Like say, if the decision maker tells me now what should be the weightage on F1 and what should be the weightage on F2. This is a two-dimensional problem. So if you just tell me weightage of anyone, then I'll be able to find out, right? So I can what combinations of this weight who gives me that particular point of this Pareto optimal front, I'll choose that. In the absence of such things, say if this solution perhaps will go to the optimization of only one objective function F1. This will also go to solutions of single objective optimization corresponding to F2 alone. Right now, we get this point calling as a utopia point, but in general, for conflicting objectives, this point will not always exist anyway. So, if you, many authors say that you can take a solution which is lying in the closest distance from this point, which we call as knee point, and in the absence of any other information, perhaps you can choose this knee point as optimally traded Pareto optimal solution. A very good technique will be like, as I told you, there are methods based on entropy. Okay, and this I did not mention yesterday. Those who are interested can go through this method known as TOPSIS. TOPSIS. Please do some Google and you will get a lot of publications based on TOPSIS. Okay. In fact, see, this method is much older than the non-dominated sorting genetic algorithm or genetic algorithms for solutions of linear programming problem. Okay. There are books as early as 80s or before that on describing TOPSIS. One of the book I remember written by Wang. So whoever, you do not have to go into those details, but please type Google TOPSIS, so you'll know a statistical method which actually ranks these Pareto optimal fronts. Okay, and looking at those ranked Pareto optimal solutions, now the decision maker will be able to choose any one of these particular most preferred solutions. Okay, so now let me move on to today's topic. Please give me a minute. I think I have to connect this to charger, I think. Okay. See, linear programming problem is one of the most effective and widely used technique. Linear programming or linear. We have so basically, in the model, we seek to maximize or minimize
Professor, your
a
voice,
linear
your
objective
voice is
function
getting
subject to voice is getting cracked, is it?
voice is yeah. Now I
Okay.
think it was okay.
Is
Last
it
part
okay
was okay,
now?
but yes, it's okay now.
Okay.
Yeah.
Okay. So a linear programming model basically it will seek to maximize or minimize a linear objective function subject to a set of linear constants. So if you remember, yesterday we briefly talked about how to classify different optimization problems. Okay, so one way to classify the optimization problems is to see whether the equations, constants, and the objective functions are linear or nonlinear or mixture of both. Now, when your objective function is linear, all the constants are linear, what you have is a linear programming problem in hand. If objective function is nonlinear and constants are linear or nonlinear, you have a nonlinear programming problem. A specific case corresponds to when you have all the constants as linear and the objective function is quadratic, non-linear but quadratic only. So that case we have a quadratic programming problem. So our interest is in linear programming problem today. So we have linear objective function and set of linear constants. So these constants may be equality type constants and inequality type constants, but all linear, and also a set of bounds on the decision variable. Is my screen still visible?
Yes, your screen is visible. Introduction to linear programming.
Yes. Okay. Something popped up, so I thought something happened. Okay. Yeah, so this is what I was saying, that a linear programming problem will consist of a decision variables, okay, set of decision variables, objective function which is linear function of the decision variables, and set of linear equality or inequality constants. Again, this linear equality or inequality constants will be function of these decision variables. So basically, in a linear programming problem, you want to find these decision variables subject which maximizes or minimizes these objective function subject to these constants. So decision variables must satisfy these constants and maximize or minimize this linear function of decision variables. So here you see some examples. So you see what is common in all these formulations is that the objective function is linear, constants are all linear. And these constants are inequality or equality type, and they are all linear. So everything can be put in a
Professor, your voice is, it has vanished for a while now.
it's necessary components. It can be able to be like
I cannot hear you. I mean, it's. I think the internet connectivity is.
vector of here x1, x2, and x3. B is the right hand side vector. So B is the vector of 50, 70, and 100. So yes, please.
I think now it's fine. For the past few minutes, 2-3 minutes, your voice was not audible at all.
Now
I
it's
think
okay.
it's okay. Now it's okay.
Okay. Okay. So what I discussed here is this, that in a linear programming problem, your objective function is linear, all the constants are linear. So you can nicely put all types of linear, all these linear programming problems in the matrix form, where we find the vector x that maximizes C objective function, which can be written as C transpose x. C is the coefficients of this objective function, right? So C will be here as -2, -1. Here it will be 1, 2, 1. This is a vector of 1, 2, 1. And x is a vector with elements x1 and x2. A is the coefficient matrix of these three constants. B is the right hand side vector. And this corresponds to x1, x2, 0, or x1, x2, x3 greater or equal to 0, non-negativity restriction on x. Okay. Now, there are various types of important linear programming problems. Several real-world problems can be formulated as linear programming problem, and applications, ranges from engineering to economics to management to production planning, so on and so forth. So here is a short list of application areas, not exactly the problem, but application areas. See, allocation of resource, production scheduling, warehousing, transportation scheduling, facility location, flight crew sort scheduling. You know, so this is an important activity of all this aircrafts. Similarly, for crew members of even other transportation systems, okay, portfolio optimizations, parameter estimation, diet problem. Diet problem is another classic problems, okay, where you have to choose a diet, okay, based on certain alternatives which will fulfill your daily nutrients, okay. So this problem may appear a small simple problem when I talk about only about myself or my family, but imagine that you have to prepare a diet, say for army, hundreds and thousands of people. Okay, so they actually become now very interesting problem. Telecommunication, call routing, network design, and the traveling salesman problem, where a particular salesman has to visit, say, n number of cities. Okay, but he has to plan such a way that he doesn't visit any city twice, and he does it in a minimum time or with minimum cost. So these are all important linear programming problems from various domains.
You are not audible.
During World War II. And you can imagine that these are very important activities associated with World War. Okay, and because of their tremendous contribution to linear programming problem, they were awarded Nobel Prize in Economics in 1975. Then George Dentich developed one of the very popular algorithm for solving linear programming problem known as Simplex Method. And from our own country, in 1984, Narendra Karmakar developed another method of solving linear programming problem, which works much better than Simplex method when applied to very large scale linear programming problem. Okay, Narendra Karmakar is actually a graduate of US, and he developed this interior point algorithm while he was working with IBM USA. Okay, so these two simplex method and interior point algorithms are basically they look into the solutions from two different angles. Like simplex method is an exterior point algorithm, if you can say, and then it's an interior point algorithm. Typically, the interior algorithm so it has much higher computational efficiency compared to simplex method. Okay. So how do you now formulate a linear programming problem? So basically, let us list down the steps. So obviously, you have to first decide what are the decision variables for the problem. So after you have decided, see, deciding decision variable for a problem, for a simple problem, is not difficult. For a large scale problems, there may be so many variables that you actually have to very carefully choose what exactly are the decision variables. So the decision variables, of course, will be those which will influence the outcome of your problem. So careful choice of decision variable is important for the large scale problems. For simple problems, often you generally will have natural choice for the decision variables. But with practice, you'll be able to, decide on what should be the appropriate choice of decision variables. Once we have decided the decision variables, we have to decide the objective function, and you know that this will be a linear function of the decision variables. So whatever you maximize or minimize, that function has to be written as a linear function of the decision variables. Then you have to write down the constants. From the problem statement, you will see that some of the constants are explicitly mentioned. So they will call explicit constant, and some constants are actually implicit. For example, suppose you are finding out, say you are finding out the values of x1 and x2 such that they represent real numbers. I mean, in the sense that they cannot be 0. I mean, they cannot be less than 0. Okay. Suppose you are solving a linear programming problem related to production planning. So you want to say, if you have say 3 different products A, B, and C, you want to find out how much of A, how much of B, and how much of C I produce, such that my profit is maximum. So immediately you understand that A, B, C cannot be less than 0. They can be 0, right? Because A equal to 0 means that you do not produce A, but they cannot be negative. So such constants may not be explicitly stated, but we need to understand that those are implicit constants, and the some constants will be explicit. Let us say in that A, B, and C, you have different productions. One constant may be that the total sum of these products should not exceed this given number. So we now know that A plus B plus C should be less or equal to that given number, so on and so forth. Okay, so we identify the decision variables, we write down the objective functions, and then we formulate the constants. And the constants most could be explicit, but you have to be careful about the implicit constants as well. So now let's take a simple problem. A fertilizer manufacturing company produces 2 types of fertilizer. Type A having high phosphorus content and type B having low phosphorus content. And these 2 fertilizers can be made using these raw materials: urea, potash, and rock phosphate. So type A, to produce type A, tons required per ton of fertilizer. So to produce 1 ton of type A fertilizer, you require urea 2 tons, potash 1 ton, and rock phosphate 1 ton. Similarly, to produce 1 ton of fertilizer B, you require 1 ton of urea, 1 ton of potash, and you do not require rock phosphate. The maximum availability of urea per day is 3000 ton. The maximum availability of potash per day is 2400 ton, and that for rock phosphate is 1000 ton. Net profits per ton of fertilizer A, type A, is 30, and that for is 20. So it may be, say, consider INR per ton or any other currency per ton. Okay, unit per ton. Net profit in some unit, let us say INR or whatever. It may look a little less, right? 1 ton profit per ton is only 30, but just imagine that that is unit profit. That's profit in some unit per ton of fertilizer A and fertilizer B. So the question we now ask is, what should be the daily production? What it means is that daily how much of type A fertilizer I will produce and how much of type B fertilizer I will produce, such that my profit is maximum and my product set must satisfy all the conditions that are stated in this table. So how do I formulate the problem? So the first step, step 1, is the choice of decision variables. We need to identify the decision variables. So here, see, the decision variables is quite obvious to choose. We can say that we have to find out what is the production schedule, what it means, what does that mean? It means that how much of type A fertilizer we will produce and how much of type B fertilizer we will produce. So let those two quantities be our decision variables. So my decision variables will be X tons type A fertilizer and Y tons type B fertilizer should be produced per day. So I have to find out these X and Y. So I'm done with the decision variable. Step 2 is my objective function. So objective function will be what? Maximization of profit. So I want to find a production schedule such that my profit is maximum. So we now focus on this line, net profit per ton. Type A 30, type B 20. So I can now, I have chosen X tons of type A and Y tons of type B as decision variables. So I can quickly write my objective function as Z equal to 30X plus 20Y. Because per ton of type A will give me 30 as profit. So X ton will give 30X. Similarly, 20 ton, Y ton of type B will give me 20Y profit coming from type B. So total profit is 30X plus 20Y. So you need to maximize 30X plus 20Y. I had because this tells me how much of urea, potash, and rock phosphate are required to produce per ton of type A and type B fertilizer. So 1 ton of type requires 2 tons of urea. So 2x. So in type B, so on y is the total required of urea. Similarly, see, X plus Y is the total consumption of potash. So that should not be less or equal to 2,400. Similarly, rock phosphate is only required in type A. So X plus 0 is less or equal to 1. These are my set of constants. And this is the so that completes my problem formulation. Maximize 30x plus 20y subject to these constants as well as these constants. Okay, so let us now take a look at a slightly different problem. Refinery blending problem. So an oil refinery makes 2 blends of fuel. Let us call, you can also consider this as this being blended at our gas station. So and refinery makes two blends of fuel, call them premium petrol and regular petrol, by mixing three types of crude oils, A, B, and C. Okay. Now, so the regular petrol composition is at least 30% A, at most 50% B, and at least 30% C. So these qualifiers are important. At least, at most. Similarly, premium petrol composition is at most 40% A, at least 35% B, and at most 40% C. So at most means the maximum it can contain is 50%. Regular petrol, see, at most 50% of B. So it will be like less or equal to 50%. Similarly, at least 30% of A will be greater or equal to 30%. So while formulating at least type of okay. So what are the data? So market is at least 10,000 liters. What is the price for regular petrol is INR 80 per liter, and slightly and 85 INR per liter. Okay, so the crude oil's cost is INR per liter. For A it is 30, for B it is 40, for C it is 50, and the daily availability of crude A, crude B, and crude C are 6,000 liter, 10,000 liter, and 12,000 liter. So how to blend crude oil so that refinery can maximize its profit? So basically, what should be okay? So you want to know how do I blend A, B, C and produce these regular petrol and premium petrol so that I can maximize the profit. So what should be my decision variables? So now the decision variables, it's not difficult, but it is again not as simple as the previous problem. Can you quickly tell me how many decision variables should I choose? How many will be how many decision variables will be there? Okay, so let's look at this. So you have to produce premium petrol and regular petrol. So let us consider that X1 is the amount of crude oil A used in making premium petrol, X2 amount of crude oil B
So you are not audible. You have not been audible for just couple of minutes now.
to
Professor,
produce regular and premium petrol.
Is it possible to change your
Yes.
connection, internet connection?
Still
Your
creating
voice,
problem.
Yeah, so it's fine now,
Okay.
but after a while it
Let me.
vanishes for about 2 minutes, 3 minutes. So each slide, I think you are missing quite a few sentences.
Okay. Okay. Let me try. Let me. So I think then do I have to stop sharing? How do I
No,
minimize?
if you are changing the are you changing the connection?
Ah,
You don't have to
oh
do
yeah.
anything.
Let me change.
If it is quick, it will take care. I mean, it will just say that your connection is weak, and if you change quickly, it will immediately start you at the same spot. Does it occupy your whole screen? I mean, are you not
Okay.
able
Let me
to?
just let me try. Yes. Just let me try.
So I can see that you are moving your mouse, so you are connected. I have you, I mean, should do you need some help? So you are muted. So you are muted. You need to unmute. Yeah, okay.
Is it better now?
Yes, yes, yes.
Okay. Hopefully it will be fine now. Okay. So there will be 6 decision variables because you need to decide on how much of A, B, C will be required for producing premium petrol as well as regular petrol. So you need 6.
Professor, you are muted for some reason.
Okay.
Yeah.
Okay. So X1 amount of crude A for regular petrol and X4 amount of crude A for premium petrol.
So I think this is the problem. You are getting muted again and again for some reason. Why is that? So you are muted again. I think did I manage?
So can
No,
you?
my settings are that
Uh,
so I have unchecked mute auto entry
okay.
and I have checked allow attendees to unmute
So let
themselves.
me
So
try.
both of them.
Okay. Let's go ahead and see this. Okay. So X1 plus X4 is the A being required. It's a true block. This is a crude product. So now you can have the selling price. So the difference is the profit. So that is the function you want to maximize. Here, now you write down the constants. So the constants on availability is straightforward. X1 plus X, you just remember that X1 and X4 are the total at the crude oil A required for making regular as well as premium petrol. Similarly, X2 and X5 for crude B, so on and so forth. So now you look at this data. Crude oil A daily availability is 6,000 liter, crude oil B 10,000 liter, crude C 12,000 liter. So you can write these as X1 plus X4 less or equal to 6,000, X2 plus X5 less or equal to 10,000, and X3 plus X6 less or equal to 12,000. Okay. Now daily market demand. So that both were 10,000, right? So market demand for both is 10,000. So you can produce 10,000 liter and above. So X1 plus X2 plus X3 is greater or equal to 10,000. X4 plus X5 plus X6 is greater or equal to 10,000. Now comes this composition is bit tricky, that your regular petrol contains at least 30% A, at most 50% B, and at least 30% C. At least 30% A, at most 50% B, and at least 30% C. Note that these doesn't have to equal to 100% because they're at most, at least, etc. So how do I write this constant? So total is X1 plus X2 plus X3. And X1 amount of crude oil A is being used for regular petrol. So that cannot exceed 30%. That is at least 30%. So that cannot be less than 30%. So X1 by X1 plus X2 plus X3, that should be greater or equal to 30%, that means 0.3. Similarly, X2 for crude oil B, and that was at most 50%. So X2 by X1 plus X2 plus X3 is less or equal to 0.5. Similarly, for crude oil C, these are for regular. Similarly, you write for premium. So this is set of constants, this is set of constants, these are set of constants. These constants you can write like this. See the first one, you can write like as x1 is greater or equal to 0.3 of x1 plus 0.3 plus x2 plus 0.3 into x3, and then it can be written like this. And of course, the non-negativity restrictions or the implicit constants that x1 through x6 cannot be negative. So now you'll be able to solve this problem. Formulation is complete. So if I take help of any linear programming solver, we'll be able to solve. We'll see how to solve using MATLAB. But also, this Microsoft Excel has solver. It doesn't come activated by default, so you have to activate it. And it also solves linear programming problem. Okay, so now let us look at the graphical solutions. Graphical solution is limited to 2 variables only. So to solve a 2-variable linear programming problem graphically, of course, you must set up the objective function and constants in mathematical format. Then plot the inequality constants as equations. I'll show you how to do that. Identify the feasible solution space. That means the domain over which x1 and x2 will lie. Feasible region for x1 and x2. Then plot the objective function, and that's of course will be a straight line because it's a linear equation. Everything is linear here. Everything will be linear equation. Everything will be straight lines. The feasible region will also consist of intersection of several straight lines and determine the optimal solution. So let us see how you do that. So when you plot each inequality as equation on the graph, we'll get the feasible region. So everywhere these inequalities has been drawn as equations. Now you can have both greater or equal to type and less or equal to type constants. If the inequality constant corresponds to a constant line is less or equal to type, then the region below the line in the first quadrant is feasible region for that constant. Here, for both these equations, which corresponds to 2 different inequality constants, linear inequality constants, this is corresponding to less or equal to type constant. This straight line or this equation less or equal to type, this inequality is also less or equal to type. So for this one, let us say this one, the region below this line is feasible. Okay, this for this one, right? So the region below this line, that means entire region like this. Similarly, for this one, the region below this line is the feasible region for that particular constant. Now, when you consider both the constants, the common region is the feasible region for the decision variables x1 and x2, the shaded region. Now, if it is greater or equal to type, then the region above the line will be the feasible region for this particular case. See, this one correspond to greater or equal to type constant. So x plus y is greater or equal to 3. So this line is basically x plus y greater or equal to 3. So I plot it as x plus y equal to 3. I plot it as equation and then take this side, okay, the region above the line as the feasible region. Similarly, for this line corresponds to x plus 2y greater or equal to 4. So this entire region above this line is feasible. Again, the common region this common, which is formed by this line, and x axis, y axis. Remember, x greater or equal to 0, y equal to greater or equal to 0 are also constants. They are also bounds. So they also participate in defining the feasible region. So this entire region is feasible. Note that this is not bounded here. Here it is bounded. Here some constant are say this one is less or equal to type, but this one is greater or equal to type. So together they have all formulated, defined this common feasible region. Okay. Now, quickly one or two points about this feasible region. This feasible region is a convex set. For linear programming problem, the feasible region is always convex. So what is convex set? A set of points or a region is defined as the convex set in n-dimensional space if for all pairs points x1 and x2 in the set, the straight line segment joining them is also entirely in the set. So this is convex, but this cannot be convex because this is going outside the region. So this will be a feasible region in LPP, but this cannot be. See, because this, if you take this point here, connect them, this part will be outside this. This feasible region can be bounded like this, or it can be unbounded like this. So this is the mathematical representation of this statement, that in a convex set you take any 2 points x1 and x2, draw a straight line, that means do a linear combination like this, and the point given by this linear combination will also lie within this convex set. This will not hold true here. So linear programming problem, these constraints together will define a convex region. Okay. An objective function of linear programming problem is a convex function. Okay. So I think you know what is convex function and concave function. Okay. So the convex function is defined like this. Suppose consider the function f. A function f is convex over a region R if you take 2 points xa and xb and make a point like as you did there, alpha into x plus 1 minus alpha into x. So theta into xa plus 1 minus theta into xb. So theta is anything between 0 to 1. The function value of these linear combinations of xa and xb is always less or equal to theta into f of xa plus 1 minus theta into f of xb. If that holds true, the function is convex. If this is greater or equal to type, the function is concave. Geometrically, for see function in x1 and x2, this type of function will be convex. If you take any 2 points, join this line will always lie above this. And for concave function, this line will always lie below this line. So these two things are important for linear programming problem, that the objective function is linear and all the constants, objective function is linear and all the constants are linear. And all the constants constitute a convex region. And by definition, a straight line is both convex and concave. So now a linear programming problem is basically representing a case where your objective function is convex function because it is linear, and all the constants are forming a convex region. So you basically have a convex programming problem. You have a convex problem. So linear programming problem is the convex problem. So you immediately conclude that, and the convex, and if you have a convex optimization problem, you have a unique solution. The global optimal solution is guaranteed. So a linear programming problem will have a global optimal solution. You'll have a unique solution. Let us not confuse this with multiple optimal solution. A large-scale linear programming problem can have multiple optimal solutions. That means various values of x1, x2, x3, x4, these decision variables But for all those multiple solutions, the objective function value will be same. And this is guaranteed because the problem is a convex programming problem. And convex programming problem has many interesting properties. So linear programming problems share all those properties. Okay, let me. These are we have. Okay, we have. Okay, now let us actually quickly take an example of the linear programming problem. So let's say a chemical company. Okay, what I'll do is to save time. I'm just. I have unmuted. Okay. Okay. So let us start here. That. Okay. Let me read the problem and just go to. Do not let us not waste time with the formulation and start with the formulation. We have seen examples of formulation. So a chemical company make two types of products, product A and product B, from the same raw material using the same processing equipment. Product A and product B, the processing time required for product A is 1 hour per kg. For product B, it is 2 hours per kg. The raw materials required for product A is 4 kg per kg of product, and that for B is 3 kg per kg. It is 40 and for B it is 50. So you have to decide how much of A and how much of B should be produced to maximize profits, given the processing time and the material constants. So let us say the way we just discussed, we have formulated this problem, where x1 is the amount of product A to produce per day, and x2 is the amount of product B to produce per day. So the profit expression is z equal to 40 x1 plus 50 x2, which I want to maximize, subject to these two constants, x1 plus 2x2 less or equal to 40, for x1 plus 3x2 less or equal to 120, and x1 plus x1 and x2 both greater or equal to 0. So the first thing, we take this x1 and x2 coordinate. So these are my xy axis. And because of this x1 greater or equal to 0, x2 greater or equal to 0, you know the first quadrant is my domain of interest. Because both the x1 and x2 should be greater or equal to 0. Now let us draw the first constant. We will draw this constant as equation. So x1 plus 2x2 equal to 40. That is all right. x1 plus 2x2 equal to 40. So how will you do that? Let us put x2. Let us consider x2 equal to 0. So what is x1? x1 equal to 40. So 40, 0 is a point on this line. Similarly, 0, 20, 0 and 20 is a point on this line. So you get this and these 2 points, just draw the line. Similarly, you will now draw the next one. Okay, so before that, this once you have drawn this point, you know this is less or equal to type. So region below this is the feasible region for this particular constant. That means the region below is representing x1 plus 2x2 less or equal to 40. Any point that lies within the shaded region will satisfy this constant. Now we need to put our second constant as well. Exactly same way you put the second constant. The shaded region is the feasible region for this constant only. Now consider the common area. The common shaded region is the region which will satisfy both the constants. That means any point if you pick up from the shaded region will satisfy first constant as well as second constant. So I have now drawn the feasible region for this linear programming problem. Note the feasible region is a convex region. Take any 2 points within this, join them. No point on the straight line will go outside this region. Now, the third step was the drawing the objective function line. That means this line. So what will you do is, you basically will do the objective function line or the objective function contour. So assume the value of z, let us say I consider z equal to 800. So if I consider z equal to 800, so this line will pass through this x1 equal to 20, x2 equal to 0, and x1 equal to 0, x2 equal to 16, so that it is 800. So this, after you have identified this point and this point, draw this line. So this line will be objective function line corresponding to z equal to 800. Now you just shift this line, okay, and remain parallel to this line. All these things will represent objective function line corresponding to different values of z, right? Simple geometry. So note that any point on this line will satisfy this equation, right? Will have the value of z equal to 800. Now you see that if I move in this direction, my objective function value increases. This line is for z equal to 800. This line is for z equal to 1200. This line z equal to 1600, so on and so forth. I want to maximize this, so I definitely will choose that line for which z equal to as maximum as possible. So I would like to shift this to as much as I want, but I cannot go infinitely like that because I have to remain within the feasible region. So the maximum I can go is a line which is parallel to this or this and just touches this point. So that will be the objective function line corresponding to this optimal point. This will be identified as optimal point. See, this is what it has been done here. So after you have identified the feasible domain, you draw the objective function line and move that line parallelly. So that will be easier. And you know that each parallel line will basically represent the same equation with different values of z. So I move this equation so that I can go on increasing the value of the z, but still remain within the feasible region. So that will help us to identify the optimal point. Now, there is a nice property of, so we won't be able to prove all those things because of one time constant, but there is a nice property of linear programming problem which proves that the optimal solution will lie on any of these corner points of this feasible region. This feasible region, which basically an intersection which is made from this intersection of these linear equations, okay. So these are basically known as polyhedron, okay. An intersection of polyhedron is a geometry made up of intersection of many such straight lines. And if the polyhedron is bounded, this is that geometry is known as polytope. This is always convex region, and the solution of this linear programming problem will always lie on any one of these corner points. Note that if the objective function line coincides with any of this side, that each point on that side is a represented solution. So that represents solution on the same line of them. Now here, see we identify this point B as the optimal solution. It doesn't here. So lying on the and simply we can simply find the value of these corner points. See 0, 0. The solution is x1 equal to 0, x2 equal to 0. So definitely that will not be not something which will maximize it. So if we just find out the values of the objective functions at these 3 corner points and just compare, I can get the optimal solution. This is easy for small problems, definitely not easy for large problems. But whatever be the case, the solution will always lie on these corner points. Solution will always be identified on these corner points for a linear programming problem. In fact, that leads to the simplex method, which is an algebraic method for solutions of linear programming problem, which basically smartly evaluates the solutions of the linear program, evaluates these each of these vertices, or it basically selects those vertices which are likely to give you the optimal solution. But optimal solution will always lie on any of these vertices. So one possible way of solving a linear programming problem is to enumeration. That is, you find out the values of the objective function at each of these corner points and select the best one. But this will not be a practical or feasible solution when your objective or when you have a large scale problem. So the simplex method is a smart algebraic method which will visit minimum number of vertices to find out the optimal solution. But simplex method is also in each iteration, it is basically visiting these vertices. So it is moving from one vertex, it is moving from one corner point to another with every iteration. Okay. So if I just say, if I change the objective function from 40x1 plus 50x2, so let us say 70x1 plus 20x2. So what you have basically have done is you have changed the slope of the line. So this is the objective function line now. But still, if you move in this direction, objective function value increases. So I go on moving, and you see now B is not optimal, but this is point C becomes optimal. So if this cost coefficient of the objective function changes, the optimal solution for the linear programming problem will change. Okay. So now let us one or two simple cases, one or two special cases we'll consider before I move on to showing you the MATLAB application for linear programming problem. Now, what we have seen now is that the xy axis and the inequality constants will together constitute a feasible region, and my solution will lie within this feasible region. Now, the feasible region can be non-existent for a particular problem. That means that problem will not have any solution. It can be single point, it can be line, it can be polygon, or an unbounded area. So based on these feasible region you have, a linear program problem may be infeasible. It may have unique optimal solutions. It may have alternative optimal solutions, or it may have, unbounded solution, means that it may have like your objective function value can be increased without any bound. That means you are moving that objective function line, say, towards right, and objective function value keep on changing, and you are still remaining within the feasible region. So this will typically happen when your region is unbounded. But unbounded region doesn't mean that you'll have unbounded solution like this, particularly for minimization problem, because you can move in the other direction and you can have an unique solution. Okay. So you have these constraints. Okay, and I have drawn all these constraints. Now this LPP is infeasible because every possible solution will violate at least one of the constraints. So you do not have a shaded region such that all these constraints are satisfied. So this is an infeasible linear programming problem. Alternate optimal solution. A linear programming problem or alternate optimal solution when these objective functions which you are using to find out the optimal solution as you move in this direction, objective function value increases. I want to maximize that, so I go in this that solution. All these, so this is what we mean by unbounded solution. This entire shaded region is the feasible region. This is the objective function line. You want to maximize that. And you see, as you move in this direction, objective function value increases. So now see, it increases as you move in this direction. I cannot move further because I'll now enter the infeasible region. So this actually gives me an unique solution even for an unbounded feasible region. Okay. So now I'll move this since I have okay. I'll show you. So MATLAB basically solves a linear programming problem expressed in this format. Note that as of now, we have stated linear programming problem as minimize or maximize C transpose X subject to Ax less or equal to B. Okay, so this is not less or equal to, but this is equal to. This is equal to. So MATLAB solves a linear programming problem in this format. So we have to express your linear programming problem in this format only. And it also solves a minimization problem. So if you have a maximization problem, you have to solve at is minus minimization problem. So F transpose X. So here we call as C. So the coefficient of the objective function. If the objective function is say x1 plus 2x2, this F is 1 and 2. Ax less or equal to B is linear inequality constants, and A equality dot x equal to BQ is basically equality, linear equality. All the constants are linear, right? So this is it. MATLAB separates these two. These are linear inequality constant, and this is linear equality constant. So you have to separate these two, and accordingly you have to supply the coefficient matrix for the linear equal constant. So coefficient equal for the linear, this is the upper one. Expand it, say transpose X will basically this. The first plus X, you have to select this one. This is argument is function. This first argument is the function handle, but this F is actually basically that C transpose X, that C here, right? So this is the coefficient of the objective function. A is the matrix for the set of linear inequality constants. B is the corresponding right hand side vector. A equality is the coefficient matrix for the set of linear equality constants corresponding right hand side vector. Variables. UB is the upper bound for the decision variables, and options, as we discussed yesterday, is a structure which you can use to change some of these different patterns. And X contains the solution. That means values of x1, x2, x3, etc. Here, lin not only returns like objective function values. This is the objective function value. Exit flag, exit. What it stopped, right? Step 1 minute successfully, so on and so forth. Okay. So we basically oftentimes we require these bell and exit flag. Now let us take a quick example. is 1, 1.5, and 4. The A matrix one and three row okay. You have to call this again. Okay, so I had this call as the matter is for to convert these that is A and A, B, F coefficients, lower bound, all lower bounds are zeros. F bound, you can put upper bound, you can put I and F as infinite call. F, the objective function coefficients, A matrix, B matrix, linear inequality. I do not have linear equality constants. So I represent A equality and B equality as empty matrix. And I have used lower bound. I have not used upper bound. You can use upper bound as well, but no need. But I have this that are equal to I have lower bound. And you just, these just 5 statements is enough to solve this linear programming problem in MATLAB. And you get this as solution. So it's almost time. So what I'll do is, okay, similar 7, 11, 10, 8. B 77, 80. F, we are maximizing 8, but as is it? So minus 150 minus 175. X1 less or equal to 9. Okay. So upper bound for X1 is 9. And X2 less or equal to 6. Upper bound of X2 is 0. Call the linear programming problem. I call the linprog solver. Remember, the sequence of these arguments is important. Again, I do not have equality constants. Is the MATLAB screen visible? So and just run. Flag 1 means, the optimal solution was obtained, successfully terminated. 88, 3.89, 3.88 is the solution. Okay, so that's all from my side. Thanks for listening to me. And if you have any question, you can please ask now.
Yeah, any questions at this stage? I think connectivity was an issue in this session. IITs, I think IIT Kharagpur has most of the meetings around this time, 4:30, 4 to 4:30, 5:30, and hence the network is quite congested. So I think we have had some issues of network. But again, the slides will be available and the content is recorded, and you can look at it whenever you want through that. So I have already posted the link. This link is also available on AICTE web portal. And so there is one question from Miss S. Shobna. How to decide lower bound and upper bound?
Okay.
Professor Sarkar, can you hear me? Yeah, okay.
See, can you? Yeah, I'm audible, no? Yes. See, the
Yes.
linear programming problem. Okay, for most of the linear programming problems are based on this. These are all like real life scenarios, right? You have seen that we are formulating problems on, like, say, production planning. Okay, then your transportation problems. Okay, diet problems, etc. So they'll generally represent decision variables.
I guess we cannot hear you. Professor Sarkar, we cannot hear you. Okay. So we cannot hear you.
Can you hear me now?
Yes.
Am I audible? Am I audible?
Yes, now you are. Now you are
Right?
not.
Yes.
Yeah. Okay. Now
Okay.
you are. Now you are.
Yeah. What I was telling is this that that non-negativity restriction that you have seen, x1 x greater or equal to 0, which generally imposes the lower bound on the decision variables. Okay. More often than not, these linear programming problems will be on real life problems, real world problems, where these decision variables cannot take negative values. Okay, so those will be imposed as linear your lower bounds. If while formulating the problem you see that certain decision variables are bounded by some values, let us say if it is related to some operating conditions and this temperature cannot go this value or pressure cannot go or below this value, those will come as upper bound. Otherwise there is no upper bound, you will have only lower bound as x greater or equal to 0, in case these are representing variables which cannot take negative values. Any other question?
Yes. There is one more question. Is there any way to find subject to constraint equation, or is it an assumption? Is there any way to find dash 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 dot 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 subject to constraint equation, or is it an assumption? So Mr. Shiva Palani Rajan, is it related to the upper bound and lower bounds, or are you asking something else? You can unmute and let us know. Mr. Shiva Prasad Rajan.
No, I didn't. What is the question? I could not hear properly.
So it's in the chat window. It says, is there any way to find dot dot dot
No,
subject to
you're now your voice is dropping.
okay.
I think today we have an issue with the IT Kharagpur network.
Yes.
Yeah, can let us try one more time? Can you please say again what is the question?
So I'm reading. Is there any way to find dot 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 subject to constraint equation, or is it an assumption? So I think he's talking about this lower and upper bound.
No, I really cannot hear.
Can you look in the chat window? If you
Is
look
it
on the
possible to write on the chat box? Is there any way to
yes.
find?
If you look on the lower strip towards the right end, you will see a chat oval. If you click on that, your chat window will open.
No, this chat, it is written like, is there any way to find dot 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 subject to constant equation, or is it assumption?
So that is the question. Yes.
I think no, it's not complete. Then the question is,
Yeah. And
what is this dot dot dot? I don't understand.
Yeah. So he's not
Is there
answering
any
also.
way to find? What is the question actually? Is there any way to find dot 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 subject to constant equations, or is it an assumption?
I guess he's talking about this upper bound and lower bound. Can you speak, Mr. Shiva Palani Rajan?
Can you write again, please? Can you write the question? Can you please? Who did this? Mr. M.
Shiva Palani
Mr.
Rajan.
M. Sivapalani Rajan. Can you please write your question? Like replacing those dot dot dot.
He is not muted. He could. Can you speak? Acha, he has written. Okay. So after objective function to maximize equation, we represent subject to.
Yes, written, is it?
He is trying to rewrite, but again in incomplete sentences. How are we writing that subject to condition? Example x1 plus 3 into 2 is equal to 40.
Yeah, so those were based on those data, right? Those are based on those statements. The constants are written based on the statements in the problem.
I think he just want to ask that what is the like subject to constant, like what is the relevance of say ST, like that. Like after writing objective, like maximizing or minimization of objective function, why we write this constant equation subjected to? That's what I think. If it is for thing, he thinks that if it is an assumption or we need to write the constant equation like that, I think.
Oh, of course, we have to write the constant equation, right? Because these constraints, these constraints are only giving you the feasible region for the domain, right?
Exactly.
See, you do not have constants. Okay, let me just Professor Akshay, can I take 1 or 2 minutes to answer this question?
Sure. You can take. Although Professor Dr. Brett is here,
Well,
Dr.
let us
Stanford, but
be quick. Yeah, so I should not take. Should stop. But anyway, since he asked this question, let me.
I think let us finish this quickly and then we can go on.
Okay, so I hope this. Let us. I hope this is now. This is now visible.
Yes, it is. So your voice is not audible. Yes, screen is visible. Yes, yes.
So what I understand, like, why do we have this copy, right? I mean, it has like basic items.
So your voice is has been intermittent, but I guess
Yeah,
Mr.
I'm doing is
Palani
I'm just writing one
Rajan
line
can
on the chat box and then we'll stop.
Okay, okay. But I guess Mr. Shiva Palani Rajan can see that the constants are obtained from the problem statement itself. So the maximum availability per day, for example, in
Right,
this
right.
case is 3000, 2400, 1000, and that is what forms the constraints. So do you have it, Mr. Shiva Palani Rajan, or I guess you can because we are already 15 minutes into Dr. Stanford's time. Maybe you can just contact him with the email. I'll be okay. So he agrees. Thank you,
I have
Professor.
actually
Yes.
Yeah. So I have actually stopped the. I had a question on the chat box. Okay. So I'll stop here.
Yeah.
Sorry for again, taking few time. So
I think the
stop.
network is
Okay.
the
Thank you all.
culprit. It was really
I
a
think
shaky.
so. Network is very bad today.
But
Okay.
thanks for
Thank you, Professor.
thanks for the content. I mean, it's really nice to provide this this set of instructions with MATLAB examples, which was I think it's a contrast to the mathematical content that has been the prevalent form of talk. Anyways, thanks Professor Sarkar for joining us and sharing your knowledge. I now move on to Dr. Stanford, who has already joined us. Professor Gogulapati, do you want to take over?
Yeah, sure. I have a bit of noise on my side, so you can get started.
Okay.
So yeah.
Okay. So I don't. I mean, Professor Dr. Stanford, are you there?
Can you hear me? Okay.
Yes.
Yeah,
yes.
yeah.
So
Great.
so let me add noise from my end has gone down. So Dr. Stanford and I know each other for I don't know, maybe a decade or more, maybe. I met him when I was doing PhD and he was wrapping up his work. And then he worked with the AFRL for some time. Then he moved to NASA Langley. So he was